Thank you very much for the introduction. So as was mentioned, I'll be talking about some of the applications, a little bit about the methodology, mostly about the applications for some of the simulations we've done of separated flows. So I know this is a very diverse audience, so I'm going to try to start with something very basic about trying to explain flow separation. If you are familiar with fluid mechanics, I ask you to forgive me if this seems too simplistic. But I'll try to illustrate flow separation with just some pictures. So this is a smoke visualization of just some flow around this airfoil. This is a 2D cross-section that's shown. And what we refer to as attach, you have a free stream flow that's traveling, in this case, from left to right. And you can see from the streamlines that the flow continues in this predominant left to right fashion. Now, if you take the same airfoil and you give it an angle of attack and you incline the nose relative to the free stream here, then for the most part you see that the streamlines are still pointing in the same direction, except in this back region close to the trailing edge of this airfoil. And so if you were to look at the vectors of where the velocity field is going, up here it's still going in what is the downstream direction. But if you look close to the boundary and the boundary layer, you'll find that there is flow that is moving upstream. And so this is a separated regime. And so generally speaking, the separation point denotes the boundary between where you have flow that's traveling downstream versus flow that's going in a nominally upstream direction. And so why do you care about flow separation? So flow separation can often indicate performance losses in many different engineering applications. So one of them that you could talk about is in gas turbine engines. So many of you flew here. So this is just a schematic of a Pratt & Whitney turbofan. So this is if you were to sit on the aircraft near the wing, you'd be able to see the fan. There's a multi-stage compressor behind it. Fuel is injected in the combustor here, and then expanded in the turbine in the back. Obviously, you can't see most of this. If you look at a zoom of the combustor region, so this is downstream of the compressor, fuel is injected here. There is a diffuser that lives in between the compressor and the combustor. And the reason that this diffuser is there is because you use the diffuser to try to increase the pressure even further after the compressor. And this is done to try to increase the thermal efficiency of your gas turbine engine. If you remember your undergraduate thermodynamics class, this is idealized as a Brayton cycle. But separation in the diffuser will reduce the amount of pressure rise that you can get. And perhaps more catastrophic is that if you have a lot of unsteadiness in your diffuser, that can actually interact with the flame in the combustor. So I'll spend just a couple minutes to talk about the methodology and the formalism that we've introduced to solve these problems. So all of this is done in the context of large-eddy simulations. So we're looking for weak solutions to the Navier-Stokes equations. And the reason that we look for weak solutions is because the resolution requirements of small-scale turbulence, they're just computationally prohibitive to fully resolve. So mathematically, we low-pass spatially filter the NS equations, and we try to solve for this filtered velocity field. And this filtered velocity field is usually based on some idea of what you can afford to resolve. So that's some length scale here, delta. And if you apply this, I'm showing this, most of what I'll show you are low-speed flows. So this is in the context of incompressible flow equations. You recover terms that look like your standard Navier-Stokes equations. There are a few additional terms that arise, and these terms represent interactions between things that you've resolved and things that you don't resolve. But in practice, typically, this is not always true, but it's peculiar because although you derive this equation from some low-pass filtering of the NS equations, this filter is not specified during simulation, nor is this idea of the filter, what filter you used in the model development, or the way you derive what models you should use for these unclosed terms. And the reason the standard practice is that you assume that when you discretize these equations, that discretization acts as this low-pass filter to do the job for you. So I won't belabor these points, but the methodology that we have taken is to leverage a formal filter definition to try to give us some insights into building some new models. So we could start with some specification of a filter, but I'm going to discuss two applications of what we can use this filter definition for. So one is to estimate, this is subgrid-scale fluctuation energy. So this is how much energy is contained in scales of motions that we aren't resolving in our simulations. And we'll try to use that to drive local mesh refinement. And the general idea is that if you have regions of your simulation domain which have large estimates for this energy, then you will try to locally increase some resolution. And this has been well behaved in a variety of different flow configurations for us, particularly because you can show from this formalism that there is an upper bound. So you won't refine spuriously in regions where there's nothing interesting happening in the flow. The other application that I'll show you is from this statement, you can actually derive formal boundary conditions for your filtered velocity field, which is what you're solving for. And this becomes important if you cannot resolve near-wall turbulence. And this is often the case in external aerodynamics. For instance, flow around airfoils that I had shown in the original slide. And so this gives you a slip boundary condition that you can drive. So I'm going to describe these ideas with two validation cases. So for the local mesh refinement, I'll discuss it in the context of this stalled diffuser. And then for the weak boundary conditions, I'll discuss airfoil that's at near stall. So I'll just have one brief mention of the software infrastructure. So we're using the Charles suite of solvers. This is developed at Cascade Technologies, where I'm now one of the developers of the software suite. It's an unstructured finite volume LES solver, formally second order. On good meshes, we can get a little bit better accuracy than that. We also have some local anisotropic mesh adaptation tools that work on almost all polyhedra, almost. So I'm showing just some strong scalability for some of the low-speed calculations that we've done. So this is, for some of the cases that I'll show, these are truly incompressible calculations so that we have reasonable strong scaling efficiencies here of about 80% or so. And recently we've gone to, we're exploring a formally low Mach formulation so that we can avoid solving a Poisson equation to get a little bit better scalability. So the first case that I mentioned before is this 3D asymmetric diffuser. So this diffuser has an inclined bottom wall, which you see here, if you look at it from the side. And one of the side walls is slightly inclined, so that's this side wall. The reason that this particular geometry is chosen is that there is a companion experiment done at Stanford where there are measurements of this particular geometry that are done. You wouldn't find this geometry in practical engineering configurations. One of the peculiarities of this geometry, so what's visualized in this plot is the instantaneous separation in the diffuser. So the separation starts in the corner between the inclined bottom and side walls, and then that slowly expands throughout the volume of the diffuser. And the real enabling piece that we had was to use this local refinement technology based on our estimates. So this is what that local refinement looks like. So if you look at this bottom image, these are log scale contours of where we estimate that our resolution is insufficient because energy of our unresolved scales is high. And you find that it's mostly concentrated. This is a separated shear layer off of the bottom wall of the diffuser. And so if we take statistics of this quantity from a coarse LES, we can use that to drive local mesh refinement within this band. So this dark black band here is the increased cell count, or the increased resolution. And this is a relatively efficient process for us to increase resolution without too much cost. So for this particular case, this additional resolution only increased the total count by about 15%. So this is a visualization of a plane. So this is halfway in between the two sidewalls. This is one of the planes that the experimentalists characterized. And so you can see the formation. This faint blue line is the boundary of the separation bubbles of flow here is moving upstream. The additional resolution that we had is packed. You can see that there's some Kelvin-Helmholtz-like structure in the shear layer. And you can compare that against, this is on the same color contour of what a coarse LES looks like. There's very little structure to speak of in this separated shear layer. So as I mentioned, the primary quantity of interest for diffusers is to be able to capture what type of pressure rise you get as you march further downstream in the diffuser. So this is the pressure coefficient to describe that pressure rise. These red symbols are the experimental measurements in that midplane on the bottom wall. The black is our LES calculation, so we agree well. And this thin blue dotted line is the inviscid approximation of what you would expect an ideal pressure rise to look like in this diffuser, just as accounting for the geometry. And so the true efficiency of this diffuser is actually much less than what you'd expect in this ideal limit. You can do finer scale comparisons. So these are streamwise mean velocity profiles in that same midplane. And you can see that these are at different stations as you march further downstream in the diffuser. And you can see that eventually, close to the wall, the flow is actually traveling upstream. So there is a mean separation bubble. So we accurately predict the separation locations. I'm showing the midplane. There's an off-plane measurement closer to one of the sidewalls the experiment makes that we're able to capture that separation location as well. So a second example that I'll take you through is the issue of a stall on an airfoil. So in takeoff and landing configurations, it's not surprising that you want to drive as much lift out of your wings as possible in order to, at least in takeoff, to get you off the ground. And so the way you usually do this is you increase the angle of attack of your airfoil. And so this is the lift coefficient against that angle of attack measured experimentally for this NACA 4412. And as you increase the angle of attack, the amount of lift that you get is increasing up to a certain point. And then beyond this point, the lift you get is actually decreasing. And actually, this falls off very dramatically if you were to continue to take data on this side. What's happening is that close to this trailing edge, there is a separation bubble that's forming. Some separation is okay, but if the separation is too severe, then you say that you are stalled. And this has potentially catastrophic impacts. So this particular experiment measures a trailing edge separation at about 85 to 86% of the chord. So this is just a view of that airfoil. So that's about here. And so this has been difficult to predict with at least steady RANs. So these are lower fidelity techniques. The Nassy-Langley research turbulence modeling group, they use this as a benchmark case to assess how well their RANS models do for this case. So if you look at, these are mean velocity profiles at these dots are the experimental measurements. This line is one particular RANS model that they use. And this is one of the last measurement locations close to the edge. You can clearly see that the experiment has predicted a separated flow, and this RANS model is it's still attached, or maybe there's a very, very small separation bubble. And so the enabling piece for this calculation is that the slip boundary conditions that we derive from the LES equations really make a calculation like this possible. So what's visualized here is the surface slip velocity that we have for this airfoil. And I've removed the contours anywhere that this streamwise slip velocity is less than or equal to 0. And so that indicates either separation or that the boundary layer is fully resolved. And so you can clearly see that we predict an unsteady trailing edge separation. I'll skip ahead. So if you try to figure out exactly how close you are to the experiment, so these are some stations at 70%, 90%, 95% of the chord of our LES compared against the experimental measurements, we do predict a separation. So these are negative velocities less than 0. And the size of the separation bubble is actually well captured by our LES. If you look at the exact separation location, as I had mentioned, the experiment has separation at about 85, 86% of the chord. We're slightly delayed at 87% of the chord, but we still predict that trailing edge separation. So just to conclude, I showed some results from new models and solution methodologies. And these are really developed from revisiting the underlying formalism of LES. I've just presented those 2 test cases validated against experimental data. And I'd like to emphasize that the LES results here shown, they do constitute predictions. There are no a priori specified coefficients or calibrations in these models. There's usually a multi-resolution piece to help determine what those coefficients should be during runtime, and those are adapted during each time steps. And just a few acknowledgments. This work is really Department of Energy sponsored end-to-end. I'm very thankful for the CSGF for my support. This work was also done in collaboration with the PSAP program at Stanford. And some of most of these calculations that I've shown are really enabled by an ALCC compute allocation. And so between the PSAP program and this ALCC allocation, it really enabled this work. So thank you.